So today we have the pleasure to hear from David Trestini. David is a postdoc in Southampton and was previously in Prague in the Academy of Science for a postdoc as well. And before that, did his PhD in Meudon with Laura Bernard and in IAP in Paris with Luc Blanchet. And today, David will talk about new post-Newtonian results for compact binaries in general relativity and scalar tensor theories. So please, David, you have around 1 hour. And also, if there is any question, feel free to ask. You can also write in the chat or raise the hand, and then I will forward them to David. So please.
So thanks, Jordan, for inviting me and everyone. It's a pleasure to talk in Aveiro. Last time I came was very nice at the beginning, but unfortunately I got COVID, but hopefully I'll visit again in less tragic situations. So today I'll be presenting some results I've been working on the last year in collaboration with these people, both in general relativity and scalar tensor theories. And so the main context that we're interested in is looking at the two-body problem, where essentially, if you take two black holes or two neutron stars for two compact objects, the motion can be divided in the bound case into three stages. So we have the inspiral phase, the merger phase, and the ring down phase. The ring down and merger phase are highly nonlinear, highly dynamical, and essentially can be treated only using numerical relativity or some perturbation theory for the ring down. But I'll be instead interested in the very long inspiral phase, where we can assume that the two bodies are well separated, slowly orbiting. And so for this, we'll be using the so-called post-Newtonian theory, which is an expansion in the small velocity, relative velocity of the two objects. So in a broader context, we know that there's quite a few approximation methods or numerical methods to treat this two-body problem in different regions of parameter space. So just for the axes here, this x parameter will be an a-dimensional frequency. So x equals 0 is very widely separated or very slowly orbiting. X equals 1/6 correspond to the ISCO, and x infinity basically is like the strong field regime. Here we have an eccentricity where we have eccentricities larger than 1, which correspond to scattering configurations, and smaller than 1 to bound orbits with the special E equals 0 circular case. And we have the symmetric mass ratio here, where nu equals 1/4 is an equal mass binary, and nu goes to 0 is an extreme mass ratio binary. And basically, post-Newtonian theory I would be interested in will be exploring this corner of parameter space of small velocities, small eccentricities, and comparable mass ratios. But some of you do NR, where you're exploring this other parameters, corner of parameter space. So you can explore the whole strong field regime, but due to numerical limitations, you can't integrate over many, many orbits in the weak field regime. Self-force is very good for everything which has extreme mass ratios, but tends to break down for comparable mass ratios. And finally, you have post-Minkowskian theory, which is interested in scattering configurations and weak fields. And so, of course, all of us want to grow and overtake the other methods, but the whole goal is that these whole different methods will at some point cover the entire parameter space. So why are we interested in post-Newtonian results? Well, first of all, the results that we obtain can be used either alone. So, for example, if you're thinking of the context of LISA, if you detect, a neutron star binary or something, or a massive, which basically will take a long time to inspiral, well, you can use post-Newtonian results alone. But of course, for current detectors, we've been seeing essentially mergers or the few cycles before merger. And so we also can resum the post-Newtonian dynamics to try to incorporate some more strong field approximation. And one of the fancier resummation methods would be the effective one-body models. These dynamics also, or waveforms also enter phenomenological waveform models and can be hybridized with numerical relativity or gravitational self-force. Just in the hybridization, for the hybridization, for example, we can think of the case where we want to include the memory effect, where we really need to integrate over the whole path of the binary. And so post-Newtonian results are useful to give the good initial conditions for an NR simulation, for example. So the advantages of these post-Newtonian methods are that they're a first principle method. They are predictions, asymptotic predictions of general relativity. They're fully analytical, so we can have a good handle on them, and this will help us understand physics. And they're fast to evaluate. However, as we've mentioned, they degrade for high eccentricity and high mass ratios, and also they're only valid for the inspired phase and tend to have a slow and oscillating convergence, as we will see in some of the plots. So in this talk, I'll divide it in two parts. The first part is a review of some recent results in general relativity, where I'm going to go over a few state-of-the-art results that we've been deriving for the flux of energy, comparing with the self-force fluxes and equations of motion. And I'll take questions at the end. And in the second part, I'll be discussing post-Newtonian methods applied to scalar tensor theory, where I've been looking in particular at applying this in the case of slightly eccentric eccentric binaries, so elliptic motion. Right. So first, I'm going to do a little review of results in general relativity. And the main starting point for studying general relativity in the post-Newtonian framework is a hierarchy of scales. So when you're looking at the two-body problem, the first thing you want to do is solve the so-called conservative dynamics. So you forget about gravitational waves, you forget about anything dissipative, and you're only interested in a conservative, either Hamiltonian, Lagrangian, etc. And from that, you can get an acceleration. So you're at leading order, you get simply Newton's law for the two-body problem. But then you can add one PN corrections, which this was first found by Lorenz and Drost. By Drost, and then it was the Einstein-Infeld-Hofmann equations. And then you can extend it to 2PN, and all this Newtonian 1PN, 2PN, this is purely conservative. There are no dissipative contributions to this. Once you've obtained at some order your conservative dynamics, well, you can go ahead and compute your gravitational radiation. So at leading order, if you have Newton's law for your two-body problem, you can use Einstein's quadruple formula to compute the flux of energy, for example, at leading order. So this, of course, this flux is a 2.5 PN quantity, but when I write Newtonian here, I'm meaning the leading order in the flux. And so you can obtain the flux at Newtonian order with a 1 PN acceleration, the flux at 1 PN, etc. And once you've obtained this radiation, well, you can see how it back reacts onto the motion. And you'll find that the Newtonian flux will give a 2.5 PN. So this is V over C to the power 5. So these PN counting is essentially, 1 PN is a V over C to the power 2, and etc. And so a 2.5 PN contribution, which is the radiation reaction. This is what we call, you have the Birk-Thorne acceleration. And of course, well, this dissipative contribution will then, influence in a lesser measure your gravitational radiation at 2.5 PN relative order. So this is essentially the picture you want to keep in mind, but in practice, how this arises is from the way we solve the equations. So we have the Einstein field equations, but in the near zone, so near the particle, we perform what we call a post-Newtonian expansion, which essentially performs in small velocities and thus expands in retardation. So if you have a function of retarded time t minus r over c, you expand when c goes into infinity. And so you get a Taylor expansion, which is valid in the near zone, but blows up as r goes to infinity. Simply, this is it. More particularly, it blows up when you get to scales larger than a gravitational wavelength. Conversely, in the far zone, we can use what we call a multipolar post-Minkowskian expansion. So we solve the vacuum field equations using a multipolar expansion. And so we get a solution which is valid everywhere in vacuum, which exists where there's matter but does not correspond to the physical solution. And the exterior solution blows up when R goes to 0. And importantly, both solutions are defined up to an homogeneous solution. And in order to find this homogeneous solution, as usual, we need boundary conditions. And the boundary conditions we'll be imposing is simply an asymptotic matching. We want that the formal Taylor expansion of the near zone when expanded to infinity exactly matches the Taylor expansion of the exterior zone when expanded to 0. And this will give us our boundary condition. And this is the whole scheme is based on this. It's what we call the post-Newtonian multipolar post-Minkowskian formalism. Of course, one thing I forgot to mention is that we're imposing no incoming radiation conditions at infinity. So what's the state of the art for what we call the conservative dynamics? So in everything here, I'll be ignoring spin because it adds a lot of complications. So all of this is ignoring spin. So since we're ignoring spin, we can focus only on time-even contributions for the conservative dynamics. And there's different methods to obtain this. You have Fokker-Lagrangian, which is what we've been doing in our group. You have ADM methods. These are the methods of Damour, Jaranovsky, and Schaeffer. And effective field theory methods, Fofas-Tourani, Porto, Rothstein, Blumlein, etc. And everyone agrees currently at the fourth post-Newtonian order, where you have, in particular, the tail effects, which enter. But at 5pn order, there was this paper here, Blumlein, which claimed to have a solution, but they disagreed with this partial result here. So there are doubts about what was correct. And then you have this paper by Porto, Riva, and Yang, who claims to have solved all the problems. I'm not exactly sure, but I think they disagree with both the previous papers. And then there's this other paper with Fofa where they claim something a bit different. So I'm not in a position to say yet that this has been resolved, but it's currently investigated. And at 6pn, we have partial results here. So that was for the conservative dynamics. 4pn is the state of the art. And then for the radiation, everything was known for a long time at 2pn, 3pn, and essentially the latest results of our group is this 4pn result here. The 4.5pn piece was actually computed before because since a half integer pn order, it's easier to compute. But these are, this is our recent 4pn results. And note that, we're the only group to have this result. At 3pn, our group had a result at 3.5pn and has been recently confirmed independently by effective field theory methods at 3pn. So at 3pn, we have two groups which have been confirmed through the results. I forgot to mention that everything I've been discussing is for circular orbits, but for elliptic orbits, the results are known at 3pn as well. Now that we've discussed the radiation, we now want to discuss the radiation reaction, and this will actually be the topic of this first part of the talk. Well, one of the topics of this first part of the talk. So the radiation reaction, the equations of motion, you can either infer them from flux balance laws, but these flux balance laws are not proven, or you can compute them exactly via matching. And so they've been computed, so it's especially the second method we'll be interested in. The result was known at 3.5pn order, and at 4.5 as well, because you have some dissipative tail contributions. I'm gonna be ignoring them from now on. But at 4.5pn order, you had a claim of a result here. And in our recent paper with Luc Blanchet and Guillaume Fay, we obtained a different result, and we explained why we think this previous result is in fact erroneous. Okay, so that was a review of the state of the art. And now I'm going to present you quickly a result, the first result, which is for the flux of energy at 4.5 post-Newtonian order, which is based on these papers here. Of course, there's lots of other papers, but these are the papers I've been contributing to. You have about 10 papers to obtain this result before I started my PhD. So this is a sketch of the result, and I've spared you the worst coefficients. So yeah. So what you see in this formula, this is the energy flux. This is how much energy you're losing at square plus at infinity. And you'll recognize here the first term is Einstein's quadruple formula. X is a dimensionless frequency associated to the 2-2 frequency. This is the mode of the frequency associated to the 2-2 mode of the gravitational waveform. So this differs, in fact, at 4pn from the orbital frequency. This is why I'm insisting on this. Mu is your symmetric mass ratio, and m is your total mass. And so at leading order, you see that we have Einstein's quadruple formula, and at 0 and 1pn, essentially you can use linearized gravity to obtain the results. And this is this diagram I'm showing here. These two lines on the bottom correspond to your two black holes orbiting each other, which are emitting a graviton. All these sketches are, in my case, for illustrative purposes. They have a precise sense within the EFT formalism, but we don't need them, and so we're maybe sloppy with the diagrams, but it's for illustration. So this is at 1pn, but at 1.5pn you have what we call the tails, which appear. So your graviton is going to have a Coulomb interaction with the total mass of your binary, and the effect of this is that if you can imagine that, in first approximation your binary is emitting gravitational waves on a flat background, but in second approximation, you say, actually, our background is not flat. It's actually something like Schwarzschild. And so you have your gravitational waves, which are scattering against this background. This is exactly the tail effect. And this leads to hereditary integrals, meaning that your gravitational wave can take, arbitrary, like pieces of the gravitational wave would take, arbitrary long time to arrive to you. So they can back react, go back, and go back to you, etc. So you lose Huygens principle. 2pn scoring. At 2.5pn, you have this quadruple interaction here. So two quadruples beating against each other. And this is the origin of what we call the memory effect. So if you imagine, essentially, you take a cube of space-time where there's a gravitational wave, and this gravitational wave has a stress energy tensor, a pseudo stress energy tensor. Of course, this is gauge dependent, but it's fine. And this pseudo stress energy tensor will be able to re-radiate at second order gravitational waves. This is this effect. And now if you have two, oscillatory components which you multiply with each other, which beat at the same frequency, well, you can have non-oscillatory components that arise through interference. And this is the origin in our formalism to the memory effect, the DC memory effect. At 3pn, we have two interactions with the mass. This is what we call the tails of tails. At 3.5, lots of similar memory-like interactions, which are a bit boring. And what I've worked on is here at 4pn, where you have these. So this first diagram here is what I call the spin quadruple tail. So spin here is actually an abusive language because SI is the angular momentum of your binary. So it's your gravitational wave is back reacting not only on the mass, but also on the angular momentum. And more interesting here, these three diagrams correspond to what we call tails of memory. So you have a tail, which then becomes memory, or a memory becomes tail, something like that. And these are actually the hardest to compute because it's both cubic and you have two time-dependent quadruples here. Whereas, for example, in this diagram here, or this higher diagram here, you only have one time-dependent multipolar moment, because here is MMM, this is the mass of the binary, it's the ADM mass of the binary, and it's constant. Okay, so this is kind of an overview. And these tails of memory I've been telling you about, maybe just to go a tiny bit more into detail. The idea is that in all these diagrams, formally what happens is that you're interested in looking at propagation effects. So there's one thing you can compute, which we call these canonical moments, or vaguely equivalently source moments. And what you're interested in is computing basically the multipolar structure of your near zone. So you look at the linearized near zone and you compute this multipolar structure. Then you iterate your waveform. You get quadratic, cubic contributions, which are very complicated. And then you re-expand at infinity. And by this re-expansion at infinity, in some way, you re-linearized your nonlinear waveform, but in a different parameter. And this gives rise to so the asymptotic structure of your waveform will be described in terms of so-called radiative moments, U and V. And these radiative moments are the moments you see in your gravitational waveform and would correspond, to your LM modes, essentially. And so what we're interested in is doing, expressing these radiative moments in terms of the source moments, because we know these source moments in terms of everything, in terms of, the matter contents, the positions, velocities, masses. And so these things here are the hardest interactions we've had to do. And just to give you a quick idea, this is essentially what it is. You take a tail, take a memory, and you get tails and memory. Okay, so that was for the flux. And so lots of hard work, lots of abscons results. But why are we interested in this? Well, because we want to assume energy conservation. So if we assume this, and this is true this has been proven to be true at some lower orders, as I will be discussing later. But if we assume this to be true at every order, well, we've been able to compute the conservative mechanical energy. We've been able to compute the flux at infinity, and you can recast this equation as a differential equation on the time evolution of your frequency. So you have to be careful whether it's the gravitational wave frequency or the orbital frequency. And you actually have a choice here you have to make, which can be debated. But this choice first appears at 4 p.m. Before there's no choice. I'm not going to be discussing this, but just be aware there are some postulates in this. But unlike in the flux and energy, they're purely rigorous, but here you have some postulates. But if you make these postulates, well, you'll find essentially that you have a time evolution of your frequency, which you can integrate to get the time evolution of your phase. And this is the phasing, and this is the main observable of your gravitational wave in an interferometer. So these results at the end are extremely important for people doing data analysis in order to correctly do parameter estimations on waveforms. Okay, so this flux that we obtained at 4.5 post-Newtonian order, it's not the only recent results in the field. There's also the self-force community that has obtained the flux at second order in the mass ratio. And the way they write it is that they take the flux. Here you have Newton's, the quadruple formula, but then they subdivide the components into 1 SF parts. This is basically the flux created by a test mass on a geodesic around a black hole. And this is second order in the mass ratio, so the first correction to this. This 1SF result was known for a long time analytically. It's a very high PN order, and we're in perfect agreement. But at 2SF, it was only obtained numerically. And as I will be showing, we found good agreement for all the coefficients. So this is a first plot where the dotted line here is the self-force result. So this is only the component F2, right? I mean, F1 is already treated, so we're only looking at this component here. And so it doesn't depend on the mass ratio. It's just the formal structure of this coefficient. And here you can see the lines, all these lines are, increasing PN results. And they're not in the order you might expect. This red line is 1 PN. This blue line is 2 PN, so it's significantly worse than 1 PN. This dotted blue line is 2.5, so then it's better. 3 PN is here. 3.5 PN goes down here. And 4 and 4.5 PN are up here. So this is an illustration of how your post-Newtonian expansion, has erratic behavior. But, after a few orbits, you do see that, your 4 and 4.5 PN results are still much better than you had initially. And you should also keep in mind that here we're looking, so this is a plot in terms of the frequency variable here. And the edge of this is the ISCO, right? And this is not at all the regime we're looking at for PN. So PN is actually supposed to be valid here. And you can imagine, you can almost see that our results are getting much better in this weak field regime. So it's just that extrapolating it to very high to very high frequencies, well, you see this erratic behavior. And we were interested in looking at, do we really agree coefficient by coefficient? And so this blue line, you have a dotted line is self-force, you have this full line is the PN result, and then we look at the residuals. So we subtract the, I'm trying to look for it here. From the self-force result, the 2SF result, we subtract the 3.5 PN prediction. And so we're expecting this to agree with this, which is just the 4 and 4.5 PN pieces of a waveform. And as you can see asymptotically here, which is the region of interest, it agrees for weak fields. When you do it again and subtract the 4 PN, we're starting to hit the numerical noise of the self-force computation, but we can see that we do have, it does seem to agree here. You seem to have the same slope and the same amplitude. And when you subtract the 4.5 PN result, since we don't have a 5 PN prediction, we can't compare it to anything, but we can look at the slope. And so this is all noise, so we can't say much, but it's compatible-ish with 5 PN slope. Noting that everything here is really, like you can see, it's numerical noise, it's totally erratic. And just to finish, yeah, here we can also see that in blue up here is just the 1SF predictions, both in the gravitational self-force formalism and dotted lines and the PN and dotted lines. So this is the truncation at leading order in the mass ratio of PN in blue. And this performs very badly compared to the numerical curve in gray here, in the case of an equal mass ratio. So you want to say, of course, it's true because it's an equal mass ratio, and so we shouldn't be applying this formalism. Fair enough. But then, if you add only the 2SF contributions, so second order self-force, well, you'll find that we agree much better. And yeah, I mean, this agrees significantly better than you would expect from a self-force computation. This is a dotted line. And the PN computation at 4.5 PN is actually pretty good as well. Yeah, so that was simply to show this. One interesting feature of this comparison, though, is that although we agree on the total flux, we disagree mode by mode. So if you decompose your flux into spherical harmonics and look at the contribution of each spherical harmonic to the flux, and you compare these. So this is an example of a comparison of the 2-2 mode. And you can see that this exercise of taking residuals, I mean, it breaks down immediately here. Even like at 3 PN, we had perfect agreement before, and now we have clear disagreement. But when you sum everything together, then it suddenly agrees. So this was puzzling, but our assumption, and I think this is a reasonable assumption, is to say that this is due to the fact that we're not in the same center of mass frame. So unlike the total flux, these LM flux are not uniquely defined, and you have some mode mixing. So now there's work ongoing in the Southampton and Dublin groups to try to figure out how to make sure that we're in the same center of mass frame. And hopefully, once that will be done, we'll have agreement on these individual LM modes. Perhaps we also have to fix the BMS frame. That's to be seen if the BMS frame itself will have a significant influence on this. Okay, and to finish this first section, I'll be discussing, just showing the equations of motion at 4th and a half post-Newtonian order. So now that we've discussed the radiation, we're discussing the radiation reaction. And so we're going back to the motion of the binary, and we're looking at this acceleration here. As a reminder, at leading order, you have Newton's law. 1 PN, 2 PN contributions are conservative. And in yellow here, you have the dissipative contributions, 2.5 PN, 3.5 PN, and the new result we'll be discussing, 4.5 PN. Reminder that at 4pn, you have both conservative and dissipative contributions, which are computed in a different way and that we will not be discussing. So this is a result. I had to show it, but what do you have to read in this result? This is the 2.5pn, 3.5pn, and 4.5pn contributions to the acceleration of the first particle. So this is essentially the force or acceleration that the first particle is feeling. And this is expressed in terms of these canonical moments I told you before. At leading order, if anyone has seen the Birk-Thorne acceleration, this is exactly it. And then you have corrections to it. And we have to essentially note in this expression is that these multipolar moments M and S are known exactly at this order in terms of the positions and velocities of the two particles. So really we have all these accelerations in terms of the positions and velocities, and this is all we need. This is the full prescription of the equations of motion, and then you can go ahead and integrate this, and this will give you your motion. So this is all solved, but the reason why we keep these multipolar moments is that it will be very useful in proving the so-called flux balance laws. So what are these flux balance laws? So what we do is that in the conservative case, we have, so you're ignoring radiation, and you have conserved quantities, of course, as conservative indicates. These are the 10 Poincare invariants, which are the energy, angular momentum, linear momentum, and center of mass position of your system. And these are conserved by the conservative acceleration, which is if you take the time derivative of these guys using only the conservative acceleration, you get 0. And now we want to see what happens if you take into account the whole acceleration. And in fact, the prediction is, or the sum is that you now have quasi-conservation laws where you have to introduce fluxes. So what we say is that what you want is that the fluxes of, so you can compute the fluxes of energy, angular momentum, P, etc. at infinity. And what you want to show is that if you have quantities, you have some defined energy, angular momentum in your near zone, such that when you take the time derivative, the energy, for example, that is lost corresponds exactly to the flux as infinity. So you might say this is obvious, and this is obvious with one definition of energy. So if you define, for example, your energy as your integral over the Landau-Lifshitz pseudotensor, then this is obvious. But what's not obvious is to say that the integral of your Landau-Lifshitz pseudotensor corresponds to the mechanical energy of the conservative system plus these terms here, which I'll be discussing here. So the map between the conserved energy that we know and the conserved energy which enters the flux balance law is not obvious. And for now, we only know how to show this with post-Newtonian accuracy. So yeah, so that's what we'll be doing. And what we've been able to show is that you have conserved quantities. So it's not, so this is all well known, but even at lower orders, but it's not the conservative energy what is conserved, but the conservative energy plus what we call a shot term. So you have to find corrections which are due to radiation reaction, but you can find such corrections such that you have a conserved energy which satisfies this flux balance law, and same for all flux balance laws. Note that in the center of mass position flux balance law, you also have the P here that appears, and this P is the total P. How do we determine these shot terms? So they're called shot terms because you have exactly the same thing that happens in electromagnetism, and this was found by Schott. And so how do you determine them? Well, what you do is that you take your conservative quantity, so H can stand for E, for example, and you take the time derivative with respect to the full acceleration. So this is not 0 because you have the dissipative contributions arising from the acceleration. But then you say, yes, but we're forgetting the flux. So you add the flux. And this is still not 0. You get an expression. And what you have to show is that this expression is actually a total derivative. And this is entirely non-trivial. It's not clear that it should be, it's the fact that it's a total derivative is the proof that we have conservation of these flux balance laws. Right. So this was an overview at this point. So now what we want to do is we want to take these two last flux balance laws here. So for P and G, which are the linear momentum and center of mass position, and we want to integrate them in order to find the time evolution of the center of mass position. So when you integrate them, you just write down integrals, and you have G of t, which depends on these two integration constants. And T0 here is the initial time before emission of gravitational waves. And we want to say now, how do we go to the center of mass frame? And the center of mass frame has to be inertial. So what we say is that in the infinite past, before radiation, well, setting G0 and P0 to 0 will set us in the center of mass frame. And then we let it evolve and see what happens. And when we let it evolve and see what happens, we find that the condition at any time to be in the center of mass frame is given by this equation, G plus gamma equals 0. And naively, what you would think is that it would be G equals 0, but it's not the case. It's G plus gamma equals 0. And this can be interpreted by the fact that your inertial center of mass frame is the barycenter not only of your matter content, because the barycenter of your matter content would be G, but also of your radiation. You have to integrate the radiation escaping at infinity and account for it in your center of mass position. And this is actually what gives rise to the kick, the gravitational kick. You get a kick because in your center of mass frame, you have radiation going on one side and your matter on the other. So remember these two quantities, pi and gamma, which are integrals of the fluxes of linear momentum and center of mass position. And what happens for a circular orbit simply is that you'll see that your center of mass position will do little circles like this as your binary evolves, if it's an asymmetric binary. But more drastically, if you have an elliptic binary or an asymmetric elliptic binary, you're going to have more gravitational waves emitted in one direction than the other. And so your whole binary is going to get kicked. So once we know how to define the center of mass frame, we want to determine transformation from any frame to the center of mass frame. And for this, we write down Gi equals gamma I equals 0. We solve this iteratively, and we'll find that at 3.5 pn, we have, so this equation here, sorry, is, so if you're in a generic frame and you have your position of your particle 1, you want a formula to express that position in the variables of the center of mass frame. And this is the formula. X is the relative position, V is the relative velocity, blah, blah, blah. And so this first piece is all well known, but we have this extra radiation contribution at 3.5 pn, which involves this gamma integral here. And using this, we can then compute the acceleration in the center of mass frame. And we find at 4.5 pn in the acceleration that we have this radiation contribution pi. And these two previous works gave the acceleration only in the center of mass frame. And for different reasons, they forgot this non-local term. And so we didn't agree with them, but because they were missing this non-local term, and we are quite certain that this non-local term needs to be included, and thus these results are incorrect. This first result here actually gives you a parametrization, and we were able to do a minimal modification of it in order to get an acceleration at the center of mass frame in a variety of gauges. So yeah, that was the main results of this first part. And maybe I can take questions now, if anyone has some on this first part.
Hello?
Yeah.
Can you hear me?
Yes.
Well, I had a few questions. Well, as you went along, I think that you answered part of them. So, but perhaps you can just add something. So the first one was actually in slide 14, when you were talking about, that you postulate energy conservation.
Mm-hmm.
Yeah, I was just kind of struck by, naively you would say, well, energy conservation should hold. But I guess there's a subtlety on the definition of what you mean by energy, as you were discussing later on in these flux balance laws.
Exactly.
So that's the issue here, right?
That's one of the issues. Another issue is that what you show is that you have also a problem with slicing, basically. So your flux you'll at second order, so at 4pn or at second order in the stuff force, your flux balance law will be slicing dependent. And you want to extract gauge invariant quantities from this, and you have, so this is kind of still I don't understand it. I mean, we've done a choice, but it's not, I don't think it's entirely understood. But for example, your flux here, if you express this flux in terms of the orbital frequency, okay, you're going to get a dependence on your choice of slicing. So for us, this choice of slicing will be an arbitrary parameter. Whereas if you express it, this flux, if you now express it in terms of the observable frequency at infinity of the 2-2 mode, this choice of slicing drops out. Conversely, the energy that we've defined before, it's an energy which is expressed in terms of the orbital frequency y, but in the conservative problem, so you don't have any radiation. So we had to basically make an assumption to say that this orbital frequency is in the conservative problem the observable, and the 2-2 mode of a flux is the observable in the dissipative problem. We had to make some association between these guys in order to get a result which was gauge invariant. But you know, you could question that choice and you'd get a different result. The computation would be just as easy, so you know, it's easily done. But yeah, it's there is an amount of choice in how you relate these things. And if you don't do that choice, and if you try to naively just write everything in terms of orbital frequency, well, you will find that it's gauge dependent, and that's not good. So
okay, thanks. I think, yeah, this slicing and this gauge dependence, it doesn't apply only here. And I was wondering about the same thing when we were discussing the center of mass frame, because as we know, center of mass is not a relativistic invariant again. So I was wondering if this is not an issue here in your discussion of the center of mass.
So we are in a setting though where we are, you know, we are perturbing around Minkowski space, and we're asymptotically flat. So in that context, I think we can define our center of mass frame property. I mean, in our formalism, we have no ambiguity. When we do this, we have no ambiguity in the definition. But in the fully relativistic context, probably it's harder to define.
Yeah, I'm not sure. You know, this discussion about the center of mass originated first in this discussion about spinning particles. You know, the Petri equation, right?
Yeah.
Yeah.
Okay.
So, and then if you have, you know, an observer, say, at the center, so where is the center of mass of a spinning particle, which is, of course, a continuous system of mass, but here you have several masses, so I guess, and then if you have an observer that moves against what you think is the geometrical center of this particle, which is extended, of course, and then you see the currents in both directions. They get their density changed in a different way, so that even if an observer originally at the geometrical center thought that that was a center of mass, an observer that's boosted with respect to the first one will actually think the center of mass is deviated to one of the sides. Okay. So, but you're saying, okay, this is asymptotically flat. So
I think this is all for the asymptotic observer.
Mm-hmm.
I'd say.
Right. So it must be addressed with respect to infinity somehow. That's what you're saying. And there is a well-defined observer addressed with respect to infinity because it's asymptotically flat.
Exactly.
Okay, maybe. Okay, maybe I'll buy your argument.
In any case, for now, like in this computation, like in practice, we found, you know, there was no ambiguity in this definition. And one interesting feature is that, so you see these flux balance laws that we obtained and we proved at 2pn order. Just going to your previous question, we're using them at 4.5pn order. So that's the assumption, but they're proven at 2pn. And so these guys, if you take the wrong center of mass, if you write GI equals 0 and try to solve this, sorry, I'm going everywhere. If you try to solve this equation, assuming GI equals 0, so if you cross out this RI term, well, what you'll find is that when you can write down this acceleration, you can compute the energy in the center of mass frame, the flux in the center of mass frame. And when you want to try to verify that the flux balance law is still conserved, you'll find it is not, because you're not in an inertial frame for the asymptotic observer. And only when you do this thing correctly and put yourself in this inertial frame will you find that also in the center of mass frame you have the same energy conservation law. So there's many indications showing that this is all correct.
Yeah, but as you pointed out, energy
conservation I understand.
Can be subtle in itself. So
I understand, but what I'm saying is that we're in a certain context, which is post-Newtonian, asymptotically flat for an asymptotic observer, which is well defined. In which case, I think all these things are clear. But as soon as you go in the fully relativistic and not necessarily asymptotically flat context, well, it's more difficult.
Yeah, and this is already sufficiently difficult. But let me just ask one final question out of my curiosity. So in slide 16, you were showing this erratic behavior that was to me a bit striking as you were adding post-Newtonian orders, and the curve as you get to larger x is becoming oscillating. So this just triggered the question in my mind. Perhaps here, but also in general, what's known about the convergence of these PN series? These terms are, of course, becoming smaller and smaller in some sense, at least in the regime where they should be valid. But what's about convergence?
I think there's no proof of anything because we don't. It's not as if we had the general term. So I think there's no proof. There are debates. I think most people think it's an asymptotic series, which means that probably at some point, at some PN order, going beyond that PN order will make it diverge. But so then you have an optimal point. So I've seen a paper. I think was it Nico Younes, who had a paper claiming that the optimal point was probably like, I don't know, 2 or 3 PN or something. But clearly here, it seems that the 4 and 4.5 seem to work better than 3 and 3.5. So yeah, I think it's hard to know anything about the series before we start. If we start seeing that the series starts diverging again, we have indications that it's an asymptotic series and that we've passed the optimal point. If it doesn't, it's hard to say. We don't know. But what I like to insist on is that divergent series can be resummed very well, and all this PN formally are statements about the asymptotic properties of GR. So these coefficients, this is a prediction of GR. And then depending on if it's what type of series it is, well, you'll treat it differently to get the best approximation. But this resummation is kind of a guess, and what we're giving is a first principle prediction about the asymptotic structure.
Right. Well, in QED you have an asymptotic series, and it's quite successful, as we know.
Exactly.
So,
exactly.
But yeah, that kind of just goes into another general question is. Which is until which order is this program rewarding, right? And which is not only related to that fundamental question, but also a practical one, which is the sort of corrections you're getting and in which circumstances it could be important. But perhaps we can discuss that more to the end of your talk, and you can continue the second part.
Well, just to answer that quickly, and then I'll continue unless anyone else has a question. But what I like to say is that there's a practical question of, are these PN predictions useful for observatories? And this is a bit, every time I ask the question, they say compute it and we'll tell you. So it's kind of, it kind of bites its tail. But I think that I've illustrated with this, this, for example, where was it? The self-force, so already the self-force comparison here, we have probably with center of mass frame, or these extra non-local terms that basically in PN, you also have value and that's what I was saying maybe in one of the first slides actually here, it helps understand physics. And so you have these new effects which appear and can inform other methods. And so I think it's very rewarding in that sense, is that we can understand lots of things, even if they are, maybe not observable, but the same kind of effects will happen in the self-force iteration, for example. So yeah, I think that's one of the motivations as well.
Okay, it's a fair point. Thank you.
Right. So I think I've kind of I'm a bit over my time. So I'll kind of try to, I have basically material for half an hour, so I'll try to shorten it drastically. So I'm going to quickly just be talking about this post-Newtonian methods applied to scalar tensor theories. So the theory I'm interested in is this one. So it's Brandstücke with time-dependent omega. You have a dynamical term for a scalar field, which couples to your Ricci scalar. And importantly, since you are modeling your particles as point particles, you have to account for the weak equivalence principle, which states that the masses of each particle can now depend on the local value of the scalar field. So our matter action will be a point particle action, but with phi-dependent masses. And then we can set up a perturbation scheme where we do a conformal transformation. We have a tensor h mu nu, which is related to a conformal metric and a scalar perturbation. And okay, so this is what we are going to be working with. And all the arbitrary functions that appear are going to be Taylor expanded because we're doing post-Newtonian. So you have omega 0 prime, but also these sensitivities, which tell you how your masses change with the scalar field. And if you see all of these horrible coefficients, you'll see that these are basically combinations of the previous ones. Note that Noether theorems tell you that if you have two black holes in this theory, you exactly recover general relativity. Skip this because we're out of time. So previous results. So in during my PhD with Luke and Laura, we worked on obtaining results for circular orbits. So we obtained the phasing at 1.5 pn for circular orbits. That actually means 2.5 pn beyond the leading dipolar contribution. And so, of course, this leading dipolar contribution, which appears in scalar tensor theory, means that it's very constrained, but that's how it is. And as you can see, these are our PN predictions in purple, and in green is a numerical simulation by Sijung Ma and others. And you see that we actually have pretty good agreement. And actually on this third plot, you see that the amplitude isn't quite right. But if you just chuck off a half PN order, the amplitude now is better. So this is kind of, I think, an illustration of also the erratic behavior of the PN series. And I'm expecting that if you add a half PN order, you'll get something much better here. Same for DC terms. And so I wanted to simply extend this work to the case of elliptic binaries. So when you have a two-body problem in either GR or these theories, at leading order, you have Newton's acceleration. And the solution of the equations of motion is an ellipse with an eccentricity and semi-major axis, which are related to your energy and angular momentum. But what you're actually interested in is not only the form of the trajectory, but also its time dependence. And for this, we introduce, so that things can be written in closed form, we introduce what we call the eccentric anomaly, which is our affine parameter. And we can write our relative radius, our time, and our angle, or azimuthal angle. These are all planar configurations because we have no spin and no precession. We can write all of these three in terms of this affine parameter, which is the eccentric anomaly. We can define, some higher order functions, true anomaly from it, etc. But anyway, this is the standard Kepler equation, which is known since centuries. And so we can ask, what happens if we now want to solve these equations of motion, but with 1 PN corrections? And Damour and Duruel actually found an elegant solution to it, where they find that it's the same thing, except that you have to, K here is 1 plus something small, and it accounts for your periastron precession. And you have a lift in your degeneracy between your eccentricities. So before you had only one eccentricity in all three equations, and now it's 3 different eccentricities. And of course, you have corrections to your other parameters. And then you can ask what happens at 2pn, and when you're at 2pn, well, you have extra terms here, which depend on this true anomaly. And so in this work, the first work I did was determining the quasi-Keplerian parameters, not in GR, but in scalar tensor theory. And simply what I want to stress for people who might be working on some other theories is that the results that I've obtained are actually useful for many theories. So in what sense? Imagine you have a theory, your favorite theory, and you can study it in a post-Newtonian sense and obtain, with some post-Newtonian accuracy, its energy and angular momentum in terms of the positions and velocities. Since it's post-Newtonian, in general, you can invert this, and you can write the time evolution of your separation angle as a function of your energy, angular momentum, and separation. And it so happens that in GR and scalar tensor theory, this is the structure that you get. A, B, C, and F are Newtonian quantities. If you now consider 1pn corrections, you get D1 and I1. No, D1, D2, and I1, I think. And as you go to higher orders, you get higher orders in your polynomial. So if you now have another theory, which happens to have this property, you can use the results. And so what we do is that I want to obtain a parametrization in terms only of this A, B, C, D, etc., so that you can use it for any other theory. And so, for example, I'll find that your semi-major axis is expressed in terms of A, B, C, D like this. And then I know for scalar tensor theory that B can be expressed in terms of your scalar tensor parameters, your energy, etc., like this. So yeah, so that was just the pitch. But why are we interested in getting this? Well, essentially the idea is we want to get the fluxes, we want to get the fluxes at high order and the secular evolution of the orbital parameters. This was done in a recent paper, but since I don't have time, I'll just be presenting the leading order. So at leading order in general relativity, Peters has shown for an elliptic orbit that if you write down a flux balance argument, so you have your Newtonian energy, your Newtonian flux, and you just equate them, he was able to show that the secular evolution of your semi-major axis and eccentricity follow this law here, which is Peters' law. So A and E are time dependent and vary on radiation reaction timescales, and this constant C0 prime accounts for your choice of orbit. So if at some time you have A and E, this determines your constant, and then your two things co-evolve using with this law. He also has differential equations for dA over dt and dE over dt, but this expression is quite elegant, and you can see you have very complicated coefficients here. And in scalar tensor theory, I've been able to do the same thing and found that if you evolve everything under leading dipolar radiation, you get something equivalent, but much simpler, which reads like this. And so these are the two laws. And so I've been able to, and so this is actually very useful, for example, if you want to compute the memory effect and things like that. And just to conclude, I wanted to show that studying scalar tensor theories can give you some results which are, at least in a functional form, much simpler and can be very useful as a toy model for general relativity. So I'll skip all these things, which I have absolutely no time for, and go right to the conclusion. And so, yeah, you can skip half of the second part of the conclusion and just go with the first one. And I'll take more questions if you have it.
Thank you, David. So we do have time for questions if there are. Maybe while you think, I have one actually, which is quite generic about the first part of your talk. I was wondering if these results at 4.5 PN that you get, they are going to be included in some waveform models or for data analysis, if not, what more would be needed in a way?
So yes, they are. I think they already have been included in EOB models. I mean, it's just that for example, for phenom, so you basically have two types of models which are actually used in data analysis, EOB and phenomenological. Because data analysis people, they want, in spiral merger or wave ring down models. And typically, for example, in phenomenological models, they have PN expansion for the in spiral, but then they have to calibrate things to NR. Actually, it's the same for EOB. And if you add new post-Newtonian information, you have to redo this whole calibration. So I think in some models it started being used, but there is some delay between the time where you put out this result and the time it takes for them to actually include them and recalibrate everything and see if it works better or worse, etc. So yes, it will be used, but not all models use them for now. But yeah,
okay.
These are useful for models.
Okay, thanks. But because in the very beginning for the state of the art, you were showing some disagreements, say, between various groups. So how do they deal with that? Like,
well, no one uses the 5 PN equations of motion anyway. This was at
okay.
What I was showing is here, it's the equations of motion at 5 PN, okay? But in order to get the 4.5 PN flux, we only needed the 4 PN equations of motion, which everyone agrees on. So in terms of waveform, I mean, no waveforms were computed using this 5 PN equations of motion.
I see. So are there more questions? Well, maybe another quick one from me then. So the self-force results that you were mentioning, are these results that you obtained, or are these results from like other groups that you compared with?
They're actually results from this group here. So Adam Pound is one of the people leading this with Warburton, Wardell. You also have Andrew Spires. So they have I don't have their paper is this one here. But yeah, no, it's not at all my results. It's like a 10-year effort of this collaboration between like Southampton, Dublin, Berlin, etc. So no, it's not me at all.
Well, now you're in the right place then.
Yeah, well now I'm working on this, but yeah.
Thanks.
10 years ago, I wasn't doing this. Finishing high school.
So no more questions? Well, then I think we can thank David again. And so our next seminar will be in 2 weeks. It's on the 27th, so I'm not sure if it's 2 or 3 weeks, but the next seminar is on the 27th. Will be in person. So thank you very much, everyone.
Thank you.
Thank you. Bye-bye.